Okay, good morning to all of you. My screen is visible. Anybody?
Yes, sir.
Okay. We'll see today there is a effect of source inductance. So normally, whatever we discussed so far, we assumed that source is not having some inductance or impedance, but practically there is a impedance in a source side. So in that effect we need to analyze. So whatever we discussed so far, thyristor will start conducting at an angle of alpha, and then it is going to be continue to conduct up to pi plus alpha. Again immediately another set of thyristors is going to conduct. Like this we explained the so far analysis. It may be full control converter, let us assume that. This is the output voltage waveform of a single phase fully controlled converter. It is started at alpha, then ended at pi plus alpha, then it will be 2 pi plus alpha and so on. And the device conductions are T1, T2 will conduct from alpha to pi plus alpha, then pi plus alpha to 2 pi plus alpha, there is a T3, T4 will conduct, then again from pi plus alpha, 2 pi plus alpha to 3 pi plus alpha, again T1, T2 will conduct. So this shows that the instant at which devices T1, T2 are going to turn off, immediately T3, T4 is going to fire if no impedance offered by the source. But practically it will not be so. Reason is because of the source also having some impedance, even though this we can see that at pi plus alpha, T1, T2 we are saying that the device is turned off, immediately T3, T4 will fire, but practically if source is having some impedance it will not happen, it will not change over suddenly because of source having some impedance. Then even current case also it is carrying this current and then immediately other current will carry in the case of source is not having impedance. But suppose that any particular case, let current is carried by the T1 and T2, load current, some magnitude, let assume that constant for our analysis, some magnitude is carried by the T1, T2, T1, T2. Then how long it will be up to pi plus alpha? Let assume that this is a pi plus alpha. And now, according to our previous version analysis, this waveform, immediately T3, T4 is going to fire, but it has to be turned off. But due to source inductance, this device will not turn off exactly at pi plus alpha like this. It will slowly turn off because of the inductor. Gradually it is going to be turned off. And immediately at pi plus alpha, T3, T4 will not turn on directly. From this point onwards, gradually it is going to be fire and then it will carry. So what is this instant? We can notice that here T3, T4 will fire, but there is a T1, T2 and T3, T4 in between. There is a one interval will be there. That interval we call it as a mu or a overlap angle. So that means that because of the source inductance or a source impedance, the currents T1, T2 thyristors is gradually decreasing to the zero from the load current, and then T3, T4 devices will be gradually turned on. Because of the inductance, sudden changes will not allow, and hence T1, T2 also having some current, T3, T4 also having some current during small duration. Therefore, all four devices will fire together. If all the four, according to our circuit, will show that if all the legs, two legs are there in a full controller, all the two legs are on at a time, then the load will be short circuited. Output voltage will be 0 during this instant. Once this instant is over, after mu period, then what will happen? Completely T1, T2 is going to be turn off and T3, T4 is going to be turn on. So therefore, as usual, again output is equal to same as the source. So that is the difference when you consider as a source. Now we'll see the waveforms and all. Now we can see the circuit. What is the difference of circuit full controller and this one? We consider source having some inductance, so that we represented here. Earlier we assumed that source is not cannot consider inductance value, only the load part we consider. But now if source also having some impedance, that means it is a reality. Earlier we assumed that source is not having impedance, that's the reason T1 T2 will conduct at a time, and immediately T3 T4 will fire after 5 plus alpha. T1 T2 is going to turn off. But now source having some impedance, that is the reason your operation will slightly modify. Now whenever positive up cycle, T1 T2 will be forward bias, and what is the sequence conduction? You can see that supply, it goes to the LS, then T1, then it goes to R, L, then T2 to out. Then this is our output voltage across the load. So it is same as the source voltage. Inductor will store energy. And in that equivalent circuit, what will happen? Source, inductor, T1, T2 and then loads. That is the equivalent circuit if T1, T2 is conducting. Now we can see this source, it goes to the inductor, T1, T2 and it goes to the load. So that is the loop. In that, whatever current it is passing, I am considering as a I1 current. This total at the first instant it is I1 current. Suppose if the next instant, let consider I2 or I3, because thyristor T3 is there. That's why some books they represented 3 also, correct. Only our conventional, anything is fine. I1 plus I2 or I1 plus I3, both are is equal to the I0 total current. So now if the during negative off cycle, what will happen? T3, T4 will be the forward bias. Negative off cycle means this is a plus and this one is a minus. Then it goes to the this path T3, then source, load R, L, and it goes to the T4 to out. This is the case whenever T3, T4 is on. Again source, then inductor, T3, T4 and then load. So these are the equivalent circuit of a power circuit when the T1, T2 is on and T3, T4 is on. So you want conventional, you can use T3 also, anything is fine. Now we'll see the voltage waveforms, current waveforms and all. Now we can see here during positive off cycle, what will happen? This is the positive off cycle. What are the devices are forward bias? T1, T2 is forward bias. So at an angle of alpha, we are giving firing pulse to the T1 and T2. But before that, what are the devices are conducting? T3, T4 are conducting. That's why you can see the current waveform. T3, T4 is conducting. Output voltage same as the source. Now the source is because in the previous cycle I am explaining this side. So during negative off cycle, T3, T4 is already conducting, then it carries the current. Let that current is equal to I2 current or I3, whatever notation. So this is the current passing through T3, T4. Now I am giving firing pulse at an angle of alpha. What will happen if I give the pulse to the T1 and T2, but you can see the current carried by the T3, T4 is a load current, and suddenly it will not reach us to 0 and suddenly I1 current will not reach us to the load current. What will happen? Thus current will be gradually decreasing, means I2 current will be gradually decreasing after giving firing pulse. I am saying that after giving firing pulse to T1 and T2, then current will be gradually rising. Means T1, T2 devices are going to conduct, and the instant at alpha T3, T4 is not turn off completely because of the source is having some inductance. Instantaneous changes will not allow. That's why this current will be gradually decreases. Once this current is gradually decreases, and also T1, T2 current will be gradually increasing, and finally during this instant T1, T2 is conducting because we are giving firing pulse to 1 and 2, and already in the previous interval T3, T4 is already on. Then we can notice that all the 4 devices are conducting at the same time during this overlap period. Then what is our output voltage? Load. Output means across load I want to measure. This voltage directly the leg is short circuited. That's why output voltage will be 0. So now we can mention this voltage will be 0. After that, what is that instant? After overlap period, means after this instant, we can notice the waveform. What is the observation? This I2 current is reaches to 0, means T3, T4 is completely turn off, and now this current will be gradually rises and pick up the load current. Then what is observation? You can see T1, T2 is completely turn on, and T3, T4 is completely turn off. After this interval is a overlap interval. What is the meaning of overlap interval? Incoming devices. What are the incoming devices? T1, T2 is going to fire. That means incoming device. And T3, T4 is going to turn off. That is outgoing devices. So the definition of overlap angle is incoming devices and outgoing devices together will fire some duration. That period we call it as a overlap period. That notation will represent as a mu. Mu is a overlap angle or a overlap period. Now, after mu, what will happen? Completely T1, T2 is on. Once T1, T2 is on, your output voltage same as the source voltage. How long? Up to the 5 plus alpha. Again, once the instant 5 plus alpha reaches, what will happen? You can notice that we are giving firing pulse to the T3 and T4. Already T1, T2 is in the conducting state. At 5 plus alpha, we are giving pulse to the T3 and T4. Now T3, T4 is trying to turn on, and T1, T2 is going to turn off. So, but that points will not be instantaneous. That will be slowly or gradually change over. Therefore, the current I1 current or thyristor T1 and T2 current gradually decreases, and then there is a other current T3, T4 current will be gradually rising. After again new instant, what will happen? Both devices, you can notice that T1, T2 is reaches to the 0, and T3, T4 reaches to the load current, that is I2 current. So that shows again some duration both devices are turn on. After that again only T3, T4 is on. T3, T4 is on again same as the source voltage. So that means only this duration, when you compare to RL load waveform and this waveform, in case of RL load waveform, your voltage waveform wherever you start, now your voltage waveform at alpha we started, and it will get the waveform will be like this in case of RL load. But now some duration we made it as a 0. So that means that because we started at alpha here itself. So that means it has to show some magnitude. But now I shown as a 0 in case of if you consider as a source effect. So that means during overlap period some amount of voltage is going to be reduces. Why? The amount of voltage is reduced when compared to only RL load without considering source effect. Without considering source effect, incoming devices are going to turn on immediately, and we ensure that outgoing devices also turn off at pi plus alpha, 2 pi plus alpha, 3 pi plus alpha, and so on. But once strictly speaking, because of source is having some inductance, instantaneous changes are not allowed. That's why some duration incoming devices and outgoing devices together will fire. Because of that, voltage is going to be dropped when compared to without considering source effect. Now we want to derive small expression how much magnitude is going to be dropped. That's all. How will you get? If you find average of this, and already you know average of RL load, you subtract these two also, you will get it. What is the drop? Because you derived the expression fully controlled rectifier without considering source effect. That is a 2 Vm by pi into cos alpha. We already known that. Now if you integrate this portion and subtract without source effect, and this automatically the drop is going to be obtained. So that is the magnitude is going to be dropped. For that small derivation part is there. This is important question, as well as the problems also they ask what is the overlap angle or what is the average output voltage if overlap angle is equal to 10 degrees or 5 degrees and so on. But strictly speaking, all the cases there is a overlap angle. But in our analysis case, every time we cannot consider overlap. We assumed that source is having negligible impedance or a zero impedance, but practically there is an impedance that we have to take care. So now we can notice that wherever overlap period is there, that output voltage will be zero. You can notice whether T1, T2, all the instant, positive half cycle and negative half cycle instant, this will be zero. And then that's what I mentioned. Rest of portion as usual, positive half cycle T1, T2 will conduct, the negative half cycle T3, T4 will conduct, but only overlap period all the four devices will conduct. That's why I mentioned T1, T2, T3, T4. Wherever overlap period is there, all the four devices you have to represent. Now we'll see the small derivation. You apply KVL. So for this loop, you can see this is the loop. If you apply the KVL, what you can get? V1 minus Ls di by dt, that is equal to V2 minus Ls di by dt. And you keep one side all the things. V1 minus V2 is equal to, take common of Ls, then di by dt minus di1 and di2, because two currents, that V1 and V2, we can see that V1 is Vm sin omega t, V2 is a minus Vm sin omega t, because that is a written part. Then you subtract these two things, then Vm sin omega t minus of minus Vm sin omega t, that will give as a 2 Vm sin omega t. So that's what V1 minus V2. Then I can write 2 Vm sin omega t, that is equal to Ls, and di by dt minus di by dt as such. And from that is the equation 1. Now load current is assumed constant, because I told no, for simplicity analysis load current is assumed constant. If T1, T2 is conducting, load current is I1, T3, T4 is conducting, load current is I2. Then the total current I0 current, sum of these two currents, I1 plus I2 is equal to I0. That's what I mentioned here. I1 plus I2 is equal to total current is a I0 current. And differentiate di by dt means di1 by dt plus di2 by dt, that is equal to 0. Why? I0 is a constant, so differentiation of constant is 0. And then you can see from equation 1, what I can write? di1 by dt minus di2 by dt, that is equal to 2 Vm sin omega t by Ls. So now we will get it as a equation 2 and equation 1. You can add equation 1 and 2. If I add these two equations, you can see here, let this one is a equation 2, this is a equation 1, means if we simplify this 2 Vm by Ls into sin omega. Then the minus term, if we are adding this to di1 by dt, and this is a di1 by, these two plus and minus terms will get cancelled out. So you can see here minus di2 by dt plus di2 by dt. Then what I can get? di1 by dt plus di1 by dt. The two will get will get cancelled out, and just simplification. Now we'll get di1 by dt is equal to Vm by Ls into sin omega t. Now during instant we can see our waveform. Wherever you can start, that will be, this is the magnitude, and here will be 0 and here will be 0, and we'll get like this. This is our voltage waveform, and again we'll start the next one. So this is the case of voltage waveform during overlap condition. So for that, what I am considering the instant current waveform, if I draw, what will happen during this instant? Incoming device, outgoing will be there. After that instant, the current will be like this. This is the current waveform, and again overlap period, it will be variation will be like this. Now what I represented here, I1 current through T1 T2, what will happen? Rises from 0 onwards. This is the I1 current, this is a I2 current, this is I1 current, again this is a I2 current. So now I1 current rises from 0, it is started at 0 and reaches to I0 current. I1 is equal to I2 is equal to, here once that particular instant, that will be as I or ID or I0. So that at omega t is equal to alpha, this is omega t is equal to alpha. What is I1 current? 0. We start at 0 and then gradually rising. So I1 is equal to 0. Then at omega t is equal to, this is a mu instant. This is what will happen? Alpha plus mu. Alpha plus mu. Earlier we used to say alpha, but now we started alpha will be at this point, and there is a overlap mu, and this point is a alpha plus mu. What is the current? It reaches as a I1 current. So that means I0. So all the currents are same during that. So therefore at alpha plus mu, I1 is equal to I0. Now you can integrate that portion, simple logic. So you can see that 0 to I0 integral this portion at omega t. If I represent here, if you use d omega t, I can use directly alpha to alpha plus mu. This way also you can do it. This is alpha, this is alpha plus mu, and this is a d omega t in that case. And you simplify that, I0 current is equal to this one. So in terms of now, what is unknown parameter here? I know alpha, and then Vm root 2 into Vs, omega is 2 pi f, and Ls is a source inductor value, and alpha at what instant you find, and mu is a overlap period that we have to calculate if you know the load current is a constant magnitude, and that is a one equation. Now similarly, you derive the expression for average output voltage also. So how can I find that? During overlap period, you can see that all the thyristors conduct, then output voltage will be 0. So then what is the average output voltage? Limits are changed. So whereas in the earlier case, you can see in the RL load alone, started at alpha, ended at pi plus alpha, and output is Vm sin omega t. So that is the case of only RL load. If I consider only RL load, that will be as a average expression case. But now if I consider RL load with source effect, then what will happen? The limits are same as usual, the 2 pulse converter, that's why 2 by 2 pi, but starting point instead of alpha, your waveform will start only at alpha plus mu. That's why we started at alpha plus mu, ended at pi plus alpha. That is only the difference between RL load and RL with source effect. So now earlier RL load, as I mentioned, alpha to pi plus alpha. But here at alpha it won't conduct because previous cycle devices are conducting, there is a overlap takes place. Then after alpha plus mu only device is going to fire. So therefore alpha plus mu to pi plus alpha, it is going to conduct, that is equal to Vm sin omega t d omega t. So that is the case of V out, and if I integrate this portion, you can get it average output voltage. Now you can notice the previous average output voltage and this one. Previous voltage is VDC at RL load alone. We mentioned that 2 Vm by pi into cos alpha. Now what is happened? Vm by pi into cos alpha plus cos of alpha plus mu. Now I keep these two things by comparison. I want to make it in terms of 2 Vm by pi into cos alpha minus something. Then that minus portion I call it as a drop. But what I want to do is I want to modify or simplify this equation in terms of 2 Vm by pi into cos alpha minus something factor, so that that minus portion I can represent as a drop due to source effect. But now this is actual. I need to get this one actually, but what I am getting is this one. So I simplify this equation in terms of this minus something, that then I can compare these two equations. Then this is as usual actual minus something factor is going to be dropped down. So therefore you find a simple relation. What I have to do is I have to make this cos of alpha plus mu, remove it. Then you keep this term and we'll get it that portion. From third equation, what I can write cos of alpha plus mu. I don't want alpha plus mu. I want only cos alpha term, so that I will easy to compare it. For that, from the equation 3, I can write cos of alpha plus mu is equal to that value. You can put it here. Then I will get only in terms of cos alpha. So that I will do now. You can see here from equation 3, cos of, this is equation 3 expression, and from this cos of alpha plus mu is equal to, what I can write? Cos alpha minus omega ls by Vm into I naught. Where I have to substitute this equation, you can substitute it in equation 4, because in the previous equation you can see here, yeah, I want to remove this, no, that's why replace that by this one. So now you substitute in equation 4. Then what will happen? You will get V out is equal to 2 Vm by pi cos alpha minus omega ls by pi into I naught. Now you compare with the R load equation and RL load equation. This is RL with with source and without source. This is a RL with the source inductance. What is the source inductance? Ls. I consider Ls. I got the expression is V out is this one. If I consider only RL load, 2 Vm by pi into cos alpha. Now you compare these two. What is the drop now? You can easily find drop. So drop is equal to V out with RL LS, or a simple way, and then this is a without LS, without LS minus V out with LS. That's all. So if you subtract that, what I can get drop? Omega LS by pi into ID. So this much amount is going to drop due to source inductance. So now if I consider resistance also, what will happen? That also we can see that. Now at moment, is it clear? So what we did is, this is the drop average expression, we got it with consideration of a source inductance, and we compare with without source inductance case, not a load, source case I am telling. Then we already derived the expression V out is equal to 2 Vm by pi into cos alpha, and now you compare this to this portion, I call it as a drop. That's what I mentioned. That is another way of representing the load voltage also, you can see, because in this what we can get it alpha, but actually suppose overlap angle is required, what again same thing in the previous expression, instead of cos of alpha plus mu replacement, you just replace cos alpha case. From this, what is the cos alpha? And substitute in the previous equation, you will get here alpha plus mu term. Why I want that is, some cases they may ask in a problem, what is the overlap angle? In that case, I cannot use directly this equation. If I use this equation, I don't have what is the overlap angle term here. That's why what I will do is, other way also you can do. From this equation, I can write cos of alpha plus mu is equal to this one, or from this equation cos of alpha is equal to this one. Cos of alpha is equal to, I can get this expression. So therefore you can get V out is equal to, this is the expression. So now you are to remember only three equations or three expressions. One is this one. You notice the different, very small difference. Only thing is, if I use cos alpha, you keep minus here. If I use cos of alpha plus mu, keep plus. That's it. So this is the, both equations are same, but only thing is, one equation in terms of cos alpha, other equation in terms of cos of alpha plus mu. So that is the, wherever you required to calculate average output voltage, directly you can use this, or you require to find the overlap angle, you can use to this, or else this also you can use it. These three equations are need to remember, or one step you can easily derive only the integration portion and we'll get it these three. So if you remember these three equations, you can easily solve the overlap angle problem, these two. Any one of the equation is going to be suited for the given data. They may give the data, some cases load current they may give, and then they may ask that firing angle also they may give. They may ask that what is the output voltage, or they may give load current and they may ask that what is the overlap angle, and in that case you can easily find using this expression. Like that, depends on our requirement, you choose these three formulas, only three formulas in this derivation. Now we'll see the same thing in representation of the diagrammatical also. What we noticed here, the can be conclude that load current or source inductance is increases. What will happen? Anybody? If source inductance increases, what will happen? Overlap angle will increases, because in our waveform you can see started at alpha. This is the alpha. During that it will be 0, and then it will ending like this. This is our overlap period case voltage waveform. And now if overlap angle is mu, then what will happen? This portion is more. If this portion is more, what is output? Voltage will be drop more, because we are not getting output voltage during the overlap period. That's the reason. If inductor is large, then it will store more energy. Just a minute. Now we can see the during overlap case, because of this inductor, if the inductor value is large, it will store more energy. If more energy means it will take more time to dissipate, then the overlap angle will be more. So that's the sentence, important sentence. If source inductance is increases, then overlap angle. So overlap angle increases, and the result obviously average output voltage is going to be decreases. So that is the one relation, or we can notice that. Now, so we can see that's what I mentioned here. If I naught or LS increases or load current increases also, it has to store that inductor, it will dissipate, it will take more time, and output voltage is going to be decreases. And similarly in general, so what is the drop we can represent in the different pulse number? We can see that, let's consider in this case 2 pulse converter. What is the drop we got it? For P is equal to 2, pulse number is 2, then drop expression, what you got it? Omega Ls by pi into Id. So omega Ls by pi into Id, that is the drop. Now for 2 pulse converter, Suppose for M pulse converter, what I can represent the drop? We can easily notice that. So for 2 pulse converter, that is P is 2. So that means P by 2 if I use here, what will happen? P is 2 means 2 will get cancelled, omega ls by pi into id, no? Then P is equal to 6 pulse converter. Let P is equal to 6. Let consider. Then what is the drop? Then P is equal to 6 by 2, that is a 3 omega ls by pi into id for the 3-phase case I'm telling. So like that you can, I don't know pulse number, then M pulse converter. What is the expression I can give? Drop is equal to M by 2 omega ls by 2 pi into id. This is our expression. So like that you can see this for M pulse converter, M omega ls by 2 pi into id. Now M may be 2 pulse or 6 pulse and so on. If M is 2 pulse, what will happen? Drop omega ls by pi into id, because 2 will get cancelled out. M is 6 by 2, that is 3 omega ls by pi into id, like this. So this is the drop due to source inductance. Now same thing, that's what I mentioned. No? M is equal to 2, it will get like this. M is equal to 6, will get like this. And now representing this, what is the output? Same expression, whatever we drawn the V out in the expression 2 Vm by pi into cos alpha minus omega ls by pi into id. So this expression I represented diagrammatically. So see that I want V out. How can I write V out? Just KVL. So V out is equal to 2 omega ls by pi into this 2 Vm by pi into cos alpha minus omega ls by pi into id or I naught. That is the expression. Same thing I represented in the circuit fashion. Now I used as a diode here. That shows that the current is passing like this. So that is the direction of current that represents the diode. Now same thing, I want to represent the current versus output voltage. Now you can see in the our expression, if overlap angle is 0, then current is 0. If current is 0, what is the magnitude? You will get 2 Vm by pi into cos alpha. If no overlap, as usual our expression is 2 Vm by pi into cos alpha. And then slope will be gradually decreases if you are increasing the overlap angle or current. So like that gradually decreases. And finally, if it reaches overlap angle is pi, means total is overlap, then what will happen? Output voltage will be 0, because short circuit the throughout the positive half cycle and negative half cycle, output voltage will be 0. So this is the only the representation how variation is going to be takes place in the output voltage. So initially overlap angle is 0 means total voltage as usual of RL load voltage will appear, and if overlap angle is increases, gradually slope will be decreases. And finally means overlap angle increases, drop will be increases. Finally total overlap angle is equal to pi, you will get output voltage will be 0. Now that is the about of source effect. Now the question is same thing. You can see here expression. If source is having some resistance also, then anybody, what is the expression here? What is the modification in this? Anybody guess this? Now I consider only what I call it as source inductance alone. This is the drop. If I consider source is having some resistance also, this is a resistance and then inductance and circuit as usual. Then what is the our output voltage? Anybody? Because current is passing like this now. If the some current is I naught current is passed through the resistance, what is the drop? Now you add minus I naught into R. This is the average expression. If resistor also consider source resistance or RS. Got it? This is 2 Vm by pi into cos alpha without source impedance effect. Now if I consider only the inductance, then the drop will be minus drop. If I consider resistance also, then minus I naught into R. And if I consider voltage drop across the thyristor also, then minus Vt, like this. So this is the scenario in all the cases. Suppose normal half-wave rectifier. What is average expression? V out is equal to Vm by 2 pi into R load case 1 plus cos alpha. This is the expression for R load average output voltage. But if I given in the problem, suppose when the device is conducting, there is a drop across the device, no, 1 to 1.5 volts or 2 volts. If you consider that also, your expression will get minus Vt, like that. Is it clear why I used minus Vt? Strictly speaking, there is a voltage drop across the inductor. That also you have to subtract from the output. Normal output expression is 2 Vm by 2 pi into 1 plus cos alpha in case of half-wave rectifier. Or any controller expression minus term, minus of voltage across the device. That also you can incorporate if problem is given. The data voltage drop across the device is 1 volt or 2 volts or 1.5 volts, whatever. You just subtract that. So that is the normal conventional expressions we have to use it. Now you can see problem. We'll see some of the problems. Problems are very important, as well as all data they make you only substitution of the formula. Formulas you can easily derive if you know voltage expression. If you know voltage expression, where it is started, where it is ended, keep it alpha to pi or pi plus alpha or a beta, you will get directly expression. Only one step of integration. Now, see the form problem. A single phase half wave controlled rectifier has purely resistive load of R, means here we need to remember only two things. What is the controller type of controller, and load, and also continuous or a discontinuous, depends on problem. Only these two things are important. So now we can see that there is a controller. So single phase half wave controller. So now we know the controller name. Another one, purely resistive load. So the load is a resistive load. Then calculate rectification efficiency, form factor, ripple factor, transformer utilization factor, peak inverse voltage of a thyristor for these two alphas. At alpha is equal to 45 degrees, alpha is equal to 45 degrees, then you need to find all the parameters. So these are the all the parameters I need to find. For that, you know what is the average expression. To find the efficiency, what you want, you know what is the PDC by PAC. So this is our average output side and input side. So for that we required as a what is the VDC and then VRMS. So all these formulas must be required. So in that aspect, we can see that expression for the first alpha, just you can repeat the problem by changing the alpha values. That's all the different. So one thing is there is a alpha 45 degrees you can substitute. And then what is the VDC? Now for the to write VDC, what we require? Which controller? Half wave controller. So half wave controller, you can write Vm by 2 pi into 1 plus cos alpha. Now I know the average expression. In that simple substitution, in this problem, Vs is not given. So Vs is not given, that's why you keep Vm as such. And what is the substitution? I can write 1 by 2 pi into 1 plus cos of 45 degrees. So we will get what is the V out. So that is the way we can get it. V out is equal to 0.271 Vm. Similarly, what I want, I naught also. How will you get I naught? V naught by R. That will give as an average load current. So V naught by R. So R value is given, that also not given, keep as such. So then what is next? RMS output voltage. So what is the RMS output voltage expression? VRMS. There is a other way also you can write in our case this two you can keep outside, then this Vm, that is 2 will go inside the root, will become as a 4, then formula will be pi, both are same, pi minus alpha by 4 pi plus sine 2 alpha by this 4 into 2, 8 pi whole power 1 by 2. This also same. Simplification, different books, different way. See, if we keep Vm alone outside, then you write the 2 also inside. I can make it Vm into pi minus alpha by 4 pi plus sine 2 alpha by 8 pi. So that whole power 1 by 2. So this is the RMS. Now you just substitute the data and we'll get it what is the VRMS. So this is the simplification. If you do 0.559 into VM, so that is the RMS. And similarly we can see that IRMS. How will you get the IRMS? VRMS by R. So we'll get, now I know VDC and then VRMS, IDC, IRMS. So just find the efficiency. So efficiency is P out by P in. So P out is V out into I out or VDC into IDC, and then AC power, that will be VRMS into IRMS, and simply find the efficiency. That is the first bit. Efficiency is equal to 48.62%. So this is the first bit. Second bit, what is the form factor? So form factor is VRMS by V out. So VRMS by V out, that will give as a form factor is 2.056. Then ripple factor. So what is the ripple factor formula? Root of form factor square minus 1. This, instead of writing this much, simply you can make it root of form factor square minus 1. So that will give as a ripple factor. And then value. So ripple factor, form factor square minus 1 root of. That will be 1.796. Then fourth one is RMS voltage of a transformer secondary. So that is transformer secondary, as usual primary voltage is known. You can easily find what is the transformer secondary, but anyhow supply is not given. You keep VM as such. Then RMS value of transformer secondary current, I can represent as a VRMS, IRMS and IS source, both are same. And then volt ampere rating, Vs into Is, Is is equal to IRMS. And then transformer utilization factor. So transformer utilization factor, so there is a PDC by volt amperes. So that PDC is nothing but a P out, whatever conventional. So that will give as a 0.186. Another one is a power factor. So power factor is approximately equal to transformer utilization factor. We mention like this. Then anyhow formulas will be there later problem. So peak inverse voltage of a half wave rectifier, how much voltage is connected across the thyristor when the device is off state, that you can get it as a VM, that is a maximum voltage. And now repeat the problem by changing alpha is equal to 90 degrees. So in that way we can repeat this problem. As such formulas, only wherever 45 degrees are there, you can replace to the something 90 degrees. So that's what I mentioned here. So this is not required anyhow, only 45. You just replace wherever alpha value is 45 is there, you can keep it as a 90 degrees. Now we'll see the next problem. Again the problem, you have to identify two things. What is the controller and what type of load, what is the alpha. So all these things are very important to substitute the formulas. A single phase 220 volts 1 kilowatt heater is connected across a single phase 220 volts 58 supply through an SCR. For firing angle delay of 45 degrees and 90 degrees, calculate power absorbed in a heater element. Now you can see that single phase supply, and now firing angle is given 45 degrees and 90 degrees, only power dissipation in a load. Now let's consider it is a half wave rectifier only. So first we should know what is the value of resistor, load resistor, because power is given. So what is the power? 1 kilowatt power is given, and now voltage also given in this problem. Voltage is a 220 volts. Once if you know the power and voltage, we can easily calculate the resistor. So this is the load resistance value. So that V square by P will give as a resistance value. So heater resistance. Now because it is a half wave controlled rectifier, the RMS output voltage as usual formula. Again I told no, this you can keep inside same formula. I can write pi minus alpha by 4 pi plus sine 2 alpha by 8 pi whole power 1 by 2, or as such formula you can use it. At alpha is equal to 45 degrees. You will get it as a VRMS. And then power absorbed heater element at 45 degrees, just you can make it as a formula V square by R. So this is a power absorbed by the heater element. This much power is drawn from the source. So 458 watts is absorbed by the heater element. So where it will come from the source only. That's the 90 degrees. Now we can notice the difference. So what is the power absorption at 90 degrees? 250 watts. And in this case 458. What is the observation? If alpha increases, output voltage will be decreases, power absorption also going to be decreases. For 45 degrees we need more power absorption happen, and for 90 degrees less power absorption. So that is the difference between the firing angle and output case. Now another problem, one pulse converter. What is the meaning of one pulse converter? One pulse converter is nothing but a half wave rectifier only, and is gated at a firing angle of 60 degrees. Now alpha is given, controller name also known to you, and then extension angle is given 220 degrees. That shows that beta. Extension angle is nothing but a beta. Beta is given 220 degrees. Alpha is given 60 degrees, and then supply is given 220 volts. This is a Vs supply. And what else? Determine the turn off time. So the circuit turn off time, average output voltage, and then current. For R value is given, L value is given. That means the load is a RL load. It is very clear that the load is given as a RL load case. What is the circuit turn off time? That's all. So you know the waveform of RL load. Every instant you try to remember the waveform. It is easy to solve the problems or derivation or anything. Now started at alpha, ended at beta. It is not showing continuous something. So RL load means you can end with beta, because beta is given. The value extension angle is a 220 degrees, beta is given. Then the turn off time, the device is going to be turn off at this instant. So for that omega Tc is equal to what I can write it, 2 pi minus beta. So this is the one complete cycle. If I consider, you can see this, and rest one pulse converter means next pulse will be 0, no, this will be 0. So final one full complete cycle is a 2 pi. So what is this point I want to know? The 2 pi minus this will give turn off time, that is equal to omega t, that is equal to 2 pi minus beta, that will give as a omega tc. Circuit turn off time, from this tc is equal to what I can write, tc is equal to 2 pi minus beta by omega. So this is the case of turn off time. Now I know what is the beta value, and omega is 2 pi f, and you can simply substitute, because 2 pi means full cycle 360 degrees minus 2 pi. This you can see that omega value is given directly, and divided by omega, that is 2 pi f. Now we can get it as a circuit turn off time, 7.7 milliseconds of time it is going to be turn off. And output, so output is, as you know, the average expression, that is one pulse converter, that means 2 in 1 by 2 pi. This is a 1 by 2 pi. What is the limits? Start with alpha, end with beta. That is equal to output is Vm sin omega t. Then your expression will be like this. Then substitute alpha is known to you, beta is known to you, Vm is known to you. What is Vm? Supply is 220. So root 2 into 220. So that will give by 2 pi into cos of how much? 60 degrees minus cos of degrees are 220. That's all. You just simplify this, we'll get it as a what is the value of average output voltage. So this is a 62 degrees. And then current. So once if you know the voltage, because your load resistor is given 7, then we'll get it as a current. I naught is equal to V naught by R. And similarly, you can see a same problem. You can see repeat if half-wave control rectifier has a purely resistive load and delay angle is 60 degrees. Determine the efficiency of a controller. So what will happen? You can see that in earlier case it is a RL load, but now it is the case of only R load. Then expressions will differ. Instead of alpha to beta, now you make use of alpha to pi. So in that case, efficiency is PDC by PAC, and PDC is already known VDC into IDC or VDC square by R, anything. And now VDC is Vm by 2 pi into 1 plus cos alpha, and alpha is given 60 degrees, and just substitute that alpha. Suppose this you just continue this problem instead of previous data, you just use this is another problem. Vm is not given, so if you want to continue previous problem data, you can take it. Suppose from the previous problem, if you mention, you can take it as a Vm is 220 volts, I mean Vs. But now it's not given Vs value, you keep Vm as such. Anyhow, efficiency that Vm will get cancelled out. So that is the reason they not mentioned. And VRMS, you just calculate same formula and alpha only substitution, and remaining will get it as 0.485 into em. And finally efficiency output by input, so that will give as a 24.28%. And now the next problem, you can see that it is RLE load. So all the problems, instead of half a, you change that controller name. Instead of 1 pulse, you make it as a 2 pulse and repeat. What is the data change? Only formulas, that's it. The substitution, instead of 1 pulse converter, if you keep 2 pulse converter and all, you can able to modify it. So now it is a 230 volt 50 Hz, now 1 pulse converter, and firing angle is given 40 degrees. It is not a 400, it is a 40 degrees, and the load current extension angle is 210 degrees. And find the circuit turn off time, average output voltage, and then average load current for R is equal to 5 ohms, L is 2 millihenry, one case. Another case is RLE also available. Then only formulas will, first case RL expression you can use it, second case RLE expression you can use it, that only the different. Now you can see circuit turn off time as usual of the previous formula, omega tc is equal to 2 pi minus beta, and we'll get it as a circuit turn off time. Average expression Vm by 2 pi into cos alpha minus cos beta, only formulas, that's all the data will get it. So V out or VDC, that is equal to Vm by 2 pi into what I can write, cos alpha minus cos beta. You can just substitute, you will get it as a what is the expression of average output voltage and load current divided by R. Similarly, for the second bit, you make use of RLE load, so that expression will differ. See that current alpha to beta, because discontinuous, because beta is given, and minus E term will get it. And as usual, E also given 110 volts, and we'll get it as a current. And similarly, average voltage expression, because it is a motor, I told, if RLE is used, motor expression armature voltage VA, that is equal to EB as per our machine's formula plus IA RE. This is the motor expression. Same thing, you use it here. Average current is known to you, and now V out I1, EB back MF is known, I naught is known, R is known. You will get it as a what is the expression value for average output voltage. And now we can see that full bridge. The problem, same problems, only change, you can notice all the cases. What I want to do is expression formula, VDC formula, and then VRMS formula is going to be modified. A single phase full bridge converter is connected to RL load. The input AC voltage is 220 volts 50 Hz. Average load current of 20 amperes. is a continuous. Now the mention is a continuous. Now whatever formulas we are going to use, we can use as a 5 minutes. Watch like watch. So we'll see these problems next class. I will take tomorrow also. You don't have tomorrow also. I think lab is only on 16th onwards. I'll continue in the next class. You can leave.
Sir? Sir?